Feeling any pressure today?
Yeah. Kind of a headache, the barometric pressure is changing, I think, or something like that, right? That's what they all say.
So are you that sensitive so that the weather changes outside are impacting you?
Not really. We're just trying to make this up as we go along, but yeah.
Indeed. So we don't want to talk about the pressure you have for like not getting your homework done or your parents or not being able to see the girl you like. We're talking about the pressure that we feel around us all the time due to gas particles.
Because we're talking about gas particles. This is the first video segment in our unit on gas laws, and we're going to learn about gases. And gases have 4 key variables, and one of them, of course, is pressure. So I'm going to write down pressure, and then what we want to do is we want to kind of define pressure real quickly. So pressure, you've got to think about this room or wherever you're standing is a place filled with tiny little itty bitty, super crazy tiny particles called molecules of gas. So let's get a box going here. And so what happens is these particles, they're constantly moving. And as they're moving, so there's all the gas particles, and they're moving, and you see when they hit the side of the container, they exert a pressure. Now pressure is a big fancy term. It's the force per unit area. So it's how much force in a certain area. So that's the introduction to pressure. We're going to talk more deeply about pressure next. But so there's 4 big variables. The first one is pressure. I think it's the hardest to understand. Other are pretty easy. I'm feeling pretty, should I take my shirt? No, I won't take my shirt off because it's hot in here. So the second variable is temperature. So if we take temperature and we draw another box for temperature right here, this is the temperature box. Again, we still have some particles. What's the difference between like hot and cold?
Well, so you probably know this from before, but anytime you raise the temperature, molecules in particular, move more quickly.
So you have arrows here that are kind of like this long. That's like how fast they move. But in my case, if it's hotter, then they're going to be moving faster.
So temperature makes molecules move more quickly.
So maybe that's the important thing. I want you to write that down. That the temperature is a function of how fast the molecules are moving, right? So the faster they are, the higher the temperature. The third one would be what?
Well, moles.
Moles. Now that's a big fancy chemistry word, but moles really has to do with how many gas particles are in our box. So when we talk about moles, let's have more moles. Sometimes you've got more gas particles in the box or in the balloon or whatever container you've got than in others. So the moles is how many, all right, good, how much stuff you've got. And the last one is volume, and that's just how big of a box you have. So if you've got a really big box, this is volume. And so these are the big 4 things that we're going to be studying. So we talk about gas and gas laws. There's actually laws. We're going to discover that P, T, N, and V all play a role.
So these 4 variables, they're kind of buddies. They all mess with each other all the time. If you think about yourself with a particular group of people, you act a certain way around some people and a different way around other people. So what we want to do is we want to see what happens when pressure is messed with by temperature, moles, and volume.
Isn't that kind of like peer pressure?
Oh,
pressure.
don't do that. Don't. I apologize for that.
Okay, so tell me more.
So these 4 variables, they all impact each other. And let's just talk about this for a second. So if pressure is caused by particles hitting the walls of a container, right? So I have particles in here, right? And every time that a particle hits the wall, it creates pressure.
Pressure.
So pressure. Now, if I raise the temperature, doesn't that cause my molecules to move more quickly? So watch what happens to pressure when I raise my temperature.
Pressure.
And so there's definitely a relationship between temperature and pressure. Would you all agree that if I increase my temperature, wouldn't that increase my pressure?
Yeah.
Or if I lower it, wouldn't the same thing happen?
Yeah.
So let's do this. What if I did this? What if instead of having it in this small container, what if I made it a much larger container?
Oh, and you get the same number of
molecules. What's going to happen to how often they hit the wall?
Pressure. You'd be further apart, right? So it's not going to hit the wall as much, so it's going to be a lower pressure. Yeah.
And then finally, what if we add a bunch more particles in here? What's going to happen to and by the way, we were mimicking one of these saying pressure, but simultaneously, all of these are saying pressure at the same time. But here's the thing.
If there's more of them, they're going to be hitting the side of the container more frequently. That means that they're going to have higher pressure.
Higher pressure. Now here's the thing. What if I did this? What if I raised the temperature, but I also made the volume bigger?
We have to sit and think about that one, because maybe it's going to do both. Maybe they'll cancel each other out, I guess.
And what if at the same time I added more stuff in?
Well, it'd get all confusing, right?
So I'm going to give an example that you probably encounter every day in the hallway. So you know when you're walking down the hallway and you see like a slapping circle going on and you're like, ooh, you're probably wondering what a slapping circle is.
What's a slapping circle?
I don't have to tell you guys here on camera, but it's when you see someone in the middle of a group of people and they're all slapping. And you're like, ooh, I want some of that, right? So you go in there and join in. And you realize that what you're doing really has no effect on that person. So what do? You're like,
I don't think they're going to feel very good getting slapped.
But again, one more of me in there is not really making that much of a difference. I want to know what I'm doing to that person. So what do? I'm like, guys,
should I file a claim against the government for him? What's going on?
Stop. Look what you're doing to him. Everybody stop. And so once everyone stops, then I smack them. Because then I know that again, this is not,
don't repeat
I don't recommend this. And parents that are watching this, I apologize. But if I smack him then, and that tear that goes down his face, I know that I was the one who caused that because there's no other sources that are also interfering with that. And so that's kind of what happens when we have 4 variables. All 4 of these variables are different influences on pressure. Unless I keep everything constant except for one of these variables, they're all going to mess with each other.
All right, let me see if I can understand this, Mr. Dimitrovitz. You're saying that if I want to study pressure and temperature, I keep the moles and the volume constant. So
Absolutely.
I'm just hitting one person, I'm the only one hitting them. Okay.
Exactly.
Poor example. But maybe not. Maybe that helps you understand it. But the point is you can only study it if you hold 2 of them constant. Is what you're
So,
saying.
and this is kind of how it is in life. If I ever want to compare one thing to something else, I can only have that one thing interacting with the other thing. If I have a whole bunch of other things interacting,
You can't figure it
I
out.
don't know what's actually causing that.
And that's isolating variables. It's a very big scientific principle. So it's actually correct, yeah. But so we can only do 2 at a time.
So we kind of talked about this before, but let's just think this through because there are laws that we're going to relate to these things here. But if you understand what's going on, you're going to say, Psh, I got the law
Easy,
ready.
easy.
So what if we wanted to compare, let's just go
Pressure.
pressure versus temperature, right?
So
we're
it
gonna
means
make a
the
box.
volume's the same. So the boxes will be the same in both cases. right?
Boxes are the same and,
And the number of
particles.
parts. So like 5 molecules or 7, whatever you just had in there.
So what happens if we're going to be just seeing what happens with pressure. That's the only thing we want to look for. So if I raise my temperature, what's going to happen to my particles, Mr.
Well,
Bergman?
Pressure. They're going to be moving faster, and they're going to hit more quickly. So that means if the T goes up, the P has to go up.
It's going to go up at the same time.
Yeah.
Conversely, if my temperature happens to go down,
If they go slower, then the pressure has to go lower as well.
so
Yeah.
we say that that's a direct relationship. So
Why
anytime,
does that mean? What does that mean, direct?
So directly proportional means if something happens to
Yeah.
something, the other thing does exactly the same thing
And
at the same rate.
As a side note, when we say direct, it actually means if something doubles, the other thing doubles as well. So it's actually numerical too.
Yeah.
So if you double the temperature, you'll double the pressure. If you half the temperature, you'll half the pressure.
Absolutely. So now let's take a look at.
Let's do a different one.
Let's do a different one. Let's take a look at moles versus
Moles versus pressure.
We'll keep pressure in the same spot here. Pressure versus moles. Again, the same box.
So it's going to be at the same temperature now because we want to hold temperature.
So we're holding
constant.
temperature constant,
And
and
the
we're still
box.
holding
The
the size
box
of
is
the
the
box
same
constant.
size.
So we're comparing these two. Well, if I take my 3 moles of gas and I ask, what pressure are they causing, right?
Let's call it 3 pressures.
3 pressures. It's not a thing, but let's say it's 3 pressures, right? And then all of a sudden I put in a gabillion. I get all.
Then there be a gabillion pressures
So it just kind of makes sense that the more particles you put in something,
because there's going to be more collisions. It's
the
gonna
more
hit-
collisions, more pressure.
So again, the higher the pressure, or
Would
the
you
higher
do-
the moles,
more moles.
the higher the P. And by the way, folks, Mr. Dimitrovitz has used a term or a symbol that we haven't seen before. The symbol for moles is an in. That's kind of
Oh.
weird. And so make sure that you note that when he's using this symbol in, that means moles. It's not a little m is for mass. So we ran out of letters and we called it an in. I don't know why.
That's a really good catch. Thank you for
Yeah.
that.
So all right. So we've
What
learned
if we
about so that's also direct too, right? Because
we
if you
lower-
double the number of moles, you're going to double the pressure. If you cut in half, so it's at direct and it's double, triple, half, bazillions, or whatever it might be. So we've done pressure and temperature, pressure moles. Should we do pressure and volume?
Let's do that. It's the only one that's really left for us to do. I'm gonna pass the torch over to you on this
So if
side.
we're going to do pressure and volume, all right. So I've got a box here, but now in the second case, I've got a box that's much, much bigger. So let's say they're double the size. So this has a volume of 1 and this is a volume of 2, but we're going to have 5 molecules in each.
both.
That's keeping the moles the same. So what's going to happen, Mr. Dimitrievich, to
Well,
the pressure?
look- yeah, remember
Right,
pressure-
versus volume.
Yeah, we count pressure when they hit the walls. So would you agree with me that in this case, the amount of times that they hit the wall is going to be much more, in fact, double the amount of times
Yeah.
that these hit the wall?
Because this it's bigger for them to hit. So if the volume is twice as much, the pressure here is going to be low. So, so volume
Goes up.
This is weird though. This is different than the other ones.
Yep.
Pressure goes down.
And what you just defined is what type of relationship?
This is called an inverse relationship. And an inverse relationship is just opposite. If you double one, the other one is cut in half. If you triple it, it's cut in third. Or if you cut it in third, it's tripled. So it depends on which way you go. So when you talk about an inverse relationship, one goes up, the other goes down. But it's more than that. It's mathematical. One's doubled, the other's cut in half.
And what's really interesting is, you may not have realized this, but what we just talked about are the 3 most important gas laws that we deal with. And the reality is that people spend, like really bright people, spend a lot of time trying to figure out the relationships.
So it turns out there's a master equation that puts them all together, so you actually can sort of change all the variables. But if you know that one goes up and one goes down, it turns out here's the equation. It's very simple. P1V1 over N1T1 equals P2V2 over N2T2. Now that's kind of long and convoluted.
We're going to cancel out one of the variables a lot, but yeah.
But if you, this is your initial pressure, your initial volume, number 1, this is the beginning condition, if you will, the number of moles at the beginning, number of the temperatures at the beginning, or the actual temperature. And then you do this, usually what you're doing is you're solving for one of the ones on this side. Because you're like saying, what's the new volume when you change the pressure or whatever?
And if you notice here, aren't these variables P, V, N, and T, the 4 variables we just talked about? And so essentially what we can do in this equation, just like we did in our problem, is we can hold something constant. Now if you hold something constant, like N, from one side to
Then
the
they're
other,
constant, then they are canceling.
they
So
just
it's
disappear.
PV over T.
Yeah. What if we held the moles constant and also the temperature constant?
Well, then it would just be PV equals PV.
So this monster equation, which we call the combined gas law, we're rarely going to use all 8 of these variables. In fact, we're going to very quickly become proficient at canceling out units that are constant. But this is an exciting unit. I can't even wait. Like I've been telling my students this in advance, Mr. Bergman, but some of the demos we're going to do are just outrageous. I think you're going to love this. Any parting thoughts on this?
Pressure, pressure, pressure.
Don't start slapping circles.
If you slap somebody, I'm slapping you. I'm actually going to come in and slap you. The one who slapped the slapper will become the slappee.
We're going to pretend all of this didn't happen. It's in your imagination. You guys have a blessed day.
Bye.